Before we dive into the next set of application examples, here's just a short summary recap of 1D arrays. Our key three array terms are these. Elements refer to the individual pieces of data in some array. Indices are their numerical positions within that array, and an array reference is the overall name by which we refer to the array, and it points to where that array has been stored in memory. Recall that creating a workable array involves three steps. First, we have to declare the array by giving it a name and a data type, which results in an array reference only. Then we need to instantiate the array, which is where we ask the compiler to set aside enough memory to store so and so many data typed elements. Finally, using initialization, we can set the default values of our array to the actual values we desire. To do anything with all the elements of an array, we simply use a standard for loop and iterate from 0 through the end of the array. The first element of an array is always at index 0, and the last element is always at this index, 1 less than the length of the array, and any array always makes its length available via this length parameter, which is itself an int value and not a method call. Then to do anything to or with any generic array element, we simply refer to it using this expression, with the index within square brackets. This expression represents one data element of whatever data type our array is. If it's an array of ints, then this represents one int value. If it's an array of strings, then this represents one individual string. Okay, let's resume taking a look at all the standard application examples, which can all be found in the example file array1dexamples.java and its associated demo videos. I strongly encourage you to download this example, open it up in JGrasp, and follow along as you view its demo videos. Alright, back to the examples. So to copy an array, there are two ways, the wrong way and the right way. The incorrect way is to set up some new array having the same size as the original array, then assign the original array to the new array by simply equating their array references. As we'll see visually on the next slide, this just results in two array references pointing to the same data in memory. The right way is to set up that new array having the same size as the original array, but then in a loop transferring the values of the old array to the new array element by element. This approach gives us what we want, which is two distinct yet identical sets of data in memory. Let's see both of these approaches visually. Here's the wrong way to go about copying an array. We start off by declaring and instantiating this new array, arrayCopy1, which is of the same data type and length as the original array, arrayname. In memory, we'd have this set of 5 memory elements in red, all initialized to 0 by default. But then if we simply equate our new array to our old array like so, all we're doing is equating the two array references such that they now point to the same memory, which is the storage of the original array. Now we've got two array references pointing to the same array, and this new array that we set up has been orphaned in memory. This is not what we want. Instead, here's the right way to go about copying an array, using a for loop. We start off in the same way by setting up some new array having the same data type and size as the original array. No change on that. But then we complete the copying by using a for loop to transfer the data of the original array, arrayname, over to the new array, arrayCopy2, element by element, like so inside this for loop. Because both arrays are of type double, all we're doing here is copying one double variable over to another double variable in this loop. And notice that because both arrays are of the same length, here it really doesn't matter which array's length parameter we use as this loop condition. So in this diagram down here, all we've done is individually transfer across each original array element in yellow to its corresponding array element in green. We now have two distinct arrays in memory, each with their own array reference. This is the right way of copying two arrays. Here's an example of how to go about resizing an array, which is somewhat similar to copying an array. So for starters, let's say we have this array of doubles up here on the right in yellow, and we want to expand this array by a factor of 4. In this code on the left, we start by obtaining the original array size, which is 2, then calculate the desired new array size, which will be 8. In this next step, we declare and instantiate this new array called temp, which will be of the desired size of 8 doubles. Once we've completed this step, our new array will look something like this up here on the right in green. We have an array reference called temp pointing to 8 contiguous double elements in memory, all initialized to 0.0. Then in this next step on the left, in a loop, we do an element for element transfer of data just as we did for copying an array, with one important difference. Now it does matter what the loop condition bound is, and we need to use the size of the original smaller array to perform this looping. So inside the loop here, we transfer the 2 elements of the original array to their corresponding elements in the larger array temp, as we also see here on the right. We leave the rest of the larger array untouched. And finally, in this last step on the left, we simply swap the array references. We set the original array reference to the newly allocated larger memory, which we see here on the right, and then we set the temp array reference equal to null, as we also see here on the right. When all is said and done, this expanded array is now our new array name, and it preserves the original 2 array values. Our temporary array reference is set to null, and it will eventually be garbage collected by the JVM, as will our original smaller array, which now has nothing pointing to it. This array has now been properly resized and is ready for business. Here's an example of how to check the equality of 2 arrays, and this is somewhat reminiscent of what we do to write an equals method. First, we're setting this equality flag equal to true for starters. We'll assume equality until proven otherwise. Then we would check that the 2 array lengths were equal, like so. If they're not, the array sizes differ, and there's no point to checking any further. But if we've established the arrays are of the same size, then we need to loop through the array and check the values element by element. In the comments up here, from our past discussion of comparisons, recall that these are the 3 basic types of comparisons we can perform. In our case, both arrays are of type double, so we check that the absolute value of each difference is within some numeric tolerance. The way we have this condition set up, this comparison fails if the tolerance is exceeded, so we set this equality flag to false for the first element which fails its comparison. And notice that in our loop statement, we have a compound loop condition. Not only must we be within the bounds of the array, but also our running comparison flag must also be true. Once any individual array element fails this check down here, this second condition becomes false, and there will be no more iterations through this loop. We're done at that point, because at least one array element differs between the 2 arrays. Whatever the outcome, after our if-else and our for loop, we print out the final verdict on equality. And notice that in this example we have no instance of operator as we did for the equals methods we wrote. The implicit assumption here is that we already know the arrays are of the same data type, or perhaps all this is within some method, and that method interface checks and enforces those data types. Another common application of an array might be to use it as a counter for outcome occurrences, to generate some sort of histogram. We might declare some int array having as many elements as there are possibilities to be considered, then each element would contain a count of how many times each particular outcome occurred. Let's consider one specific example, that of counting dice rolls. Yeah, I know. Programming is applied to the gambling industry, right? So let's say we consider one die, and of course it has 6 possible outcomes from 1 to 6. We declare an int array of size 6, then in a loop initialize each element to 0, which technically is already the default, but we'll do it anyway. Then to simulate the roll of one die, we could use the random class to generate a random number from 1 to 6, and we've already seen how to do this in a prior program assignment. Then the only catch is that for each roll, we need to increment the roll minus 1 array element. So for example, if we rolled a 1, we'd increment the 0 array element, not the 1 element. Here's a code example which implements what we just discussed. We declare 2 int variables, one for the number of possible dice outcomes, 6, and another for the desired number of rolls, which we'll say is some large number like 500. Then we set up this int array for the 6 possible outcomes, assuming this array has already been declared somewhere upstream. We also set up this random number generator and this int to store any 1 dice roll. In this first for loop, we explicitly initialize all 6 elements to 0, although we recognize that that's already just the default value. Then in the second for loop, we actually roll them bones the desired 500 times. For each loop iteration, this random number generator gives us back a number from 0 to 5, which we then offset by 1 to get our random dice roll 1 to 6. We then increment the appropriate count by 1, taking care to offset the array index by 1. Remember that this entire array element represents one int value, so that we are just incrementing one int value by 1. When all is said and done, in this last for loop, we again loop over the 6 elements of our dice array and print out each possible dice roll and its number of occurrences over 500 rolls. Note that again we need to offset the array index by 1 again to get these 6 possible dice values, along with each of their occurrences. If you wanted to total up these outcomes, you'd see that they do indeed add up to 500. Furthermore, 500 divided by 6 is about 83. So while this is not quite a perfect statistical distribution, most of these outcomes are in the general ballpark of 83. Crude, but close enough for illustration. And of course, every time you ran this code again, you'd get different results. As is so often the case in programming, there's often more than one way to tackle a problem, and some ways might be better or preferable than others. In the case of our counter, our version 1 approach might not be ideal. For example, we needed to subtract 1 from each dice roll to increment its count in the array. Then later, when we were looping through to display the results, we needed to add 1 back onto each array index to display which dice roll it was for. Down here on the left, we see what our memory looks like for our first counter array. This array is 6 elements long, so the array indices go from 0 to 5, but the corresponding dice rolls are offset by 1 up here. In each of these array elements are the actual counts we obtained in the previous example. So for example, if we rolled a 4, we'd need to decrement that roll to update the index equal 3 element. But later on, when looping through this array to display the results, we'd need to increment this array index equal 3 to display that this count of 60 was for a roll of 4. It works fine, but maybe it's a little clumsy. Perhaps we can improve this approach in version 2 here on the right. Now we're using an array of size 7 rather than size 6, so the array elements 1 to 6 directly correspond to the dice rolls 1 to 6, with no offsets needed now. Element 0 of our array is now some wasted space, but oh well. So this just represents a trade-off between some computational efficiency and memory space utilization. Again, there's often more than one way to tackle a programming problem. So to finish up this set of examples, here's the version 2 of our counter application. We still have the die max set to 6 somewhere upstream, so now we instantiate our item counts array to size 7 rather than size 6 as before. In this next for loop, we still explicitly initialize all 7 array elements to 0, even though we realize that's already the default value. Then in this next for loop, we once again roll the bones 500 times, and we still need to offset our random number generation by 1 to get a result from 1 to 6. But now, we can increment the corresponding count array element directly using our dice roll. Again, this entire array element represents one int value, which we are then incrementing using this shortcut operator. Finally, when we loop through our count array again to display the results, notice that now we're looping from 1 to 6, not 0 to 5 as before. And notice that we can print the dice roll and its count directly using the loop index I with no offsets needed this time, giving us this different set of results this time. Okay, well, that's it for all of these common one-dimensional array operations. Make sure to look over that source code example file because it contains all of the discussed examples, and it's helpful to run through it on your own to see how it all works. Between that example file and its associated code walkthrough video, you should have plenty of what you need to tackle most common array applications in your own code.